Okay, to start off this chapter review, I am going to go with aerial and vinyl halides as our introduction, and I'm going to kind of be comparing what we left off with in chapter 17, looking at in terms of structures, and what we are going to be focusing on in chapter 18. So in chapter 18, we're going to be looking at aerial halides and vinyl chlorides. This is again just an example of something that we could look like so we can get familiar with what that structure would look like. In chapter 17, we have an example of a benzylic halide and an allyl chloride, if I can spell. And so then we kind of moved on into SN2 reactions and differentiating substrates. So differentiating. We are going to focus on alkyl halides, which are right here. And that SN2 reaction that's going to go through is this nucleophile is going to attack, and this bromine kind of pops off, and that's kind of the standard reaction that we're pretty used to seeing. But when we look down here at aerial halides and vinylic halides, we don't necessarily see the same thing, and that's specific to this carbon being sp2 hybridized and sp2 hybridized, and we can see that this in fact does not go through an SN2 reaction, and that was kind of our big takeaway. And this happens, why? Because of changes in hybridization. So the next kind of thing that we looked at was the transition state through sp2 that we observed. And so first I'm gonna take this diagram and we're just gonna see we would have our partial negative charges, and a big key factor of this is also sp2 hybridized. And kind of a big takeaway of the transition states between alkyl halides, aerial halides, and vinylic halides is looking at the changes in hybridization. And so specifically we can look at alkyl halides and observe that they go from sp3 to sp2. Vinyl and aerial halides, however, we are going to observe that they go through sp2 to sp hybridization, and specifically in SN2 reactions, they are prohibitively slow, meaning they don't happen. The next thing we can move on into is doing kind of a review of elimination reactions of vinyl halides. And so the key things to look at this is, just in case we forgot, iso, ortho, meta, the positions of para, and also another ortho and meta. But specifically, we're going to look for strong electronegative groups. And those would be present at that iso location. And then we're also going to pay attention to anything that comes off of here, any other groups. Also, we really want to look at down here for electron withdrawing groups, because those are all going to be rate determining steps. And just to harp on this, there are a lot of rate determining steps that we went over, but this are specifically the ones that I struggled with. And so that's why I included them in this video. So the next kind of thing that we can move on to is SN1 reactions. And so we're going to go first with aerial halides. And when there is an interaction with a nucleophile, this is the intermediate that we see. And the product is we're going to see something that looks a little like this. that's pretty standard for what we've been seeing, but what happens when we look at our um, aryl and vanillic halides? I'm just going to put aryl and vanillic, and we are going to see that there is no reaction that occurs, and our intermediate, if we were to have one, would be in a solvent. So I'm just going to draw that right there, and they actually stay separate, and so there is no reaction that occurs. And the reason as to why is the instability of vinyl cations. That being there's stronger sp2 bonds than in comparison to sp3. The next kind of thing that we can move on to is a vinyl carbocation, and specifically we're going to look at the empty 2p orbitals and sp2 hybridization. So that would look right there. And when we are looking at these specific interactions of those orbitals, we see that it is high in energy, and it creates a highly unstable intermediate, or carbocation, my apologies. And that is just kind of a key thing to keep in mind when working with vinyl carbocations. So the next thing that we kind of move into is nucleophilic aromatic substitution, and specifically we're going to focus on this hydrogen right here, and we talked about how it has a really high pKa, and we called that a weak acid, a very weak acid. I'm going to just say times 3. And over here, we're going to look at this hydrogen, and this is also a weak acid, but not quite as weak as the sp3 hybridized, and so we're going to see this just times 2. And over here, I'm going to finish trying that. Sorry. And this hydrogen right there is a weak acid. It is not as weak as the other previous sp2 that's right there, but it is still weak. We can, however, look at those conjugate bases, which was a key piece that we want to make sure to look at in terms of determining if we need a strong base or not. So specifically right here, we're going to label this sp3, sp2, and sp2, or sp. And this is going to help us know whether or not we need a strong base. And that is a huge part of nucleophilic aromatic substitution. So we really need to but we need to be conscious of the pKa's and how acidic our substrates are, along with our conjugate bases. So next we're going to move on to coupling. I'm just kind of going to indicate where we see these reactions happening when there is a catalyst with an aryl halide. So we're going to focus on that carbon right there and this carbon, and you can kind of view how a reaction would occur. And this specific carbon is right there, and this second carbon is right there. And then if we move down, we can look this carbon right here, we can watch it through the reaction right there, and that's more of a field cross alkylation, which is also a key piece of a reminder that Dr. Ogar gave us earlier. So the next thing we're going to focus on is beta elimination, specifically in metals. So we're going to indicate right here, this is sp3 hybridized. There is a beta carbon right there and an alpha carbon right there. Those blue lines are just going to show kind of an overview of the mechanism. And this kind of just highlights that it has to be in a phase, and kind of the priority of this beta carbon that's, oops, my bad, that's right there. And yeah. The next thing to move into is transition metals, and we have NC ligands, and those are just MC bonds, which are metals and carbons, ML bonds, which are metals and ligands. And the two metal ligand bonds we have are neutral ligands. And we're just going to call those L. And the other type of ligand that we have are charged ligands. And those ligands we're going to give the letter X. And those often have a negative charge, but not always. And an example of one of those is our OCH3 that has a negative charge, and up here NH3, which is neutral. Another key piece is in Grignard's reagent. There is a organometallic bond to pay attention to. And this is just a part of organometallic chemistry, and hopefully learn a little more about that. But I am going to finish up with just kind of doing an overview of the catalytic cycle. We still have to go a little more in depth with hex coupling and one of these other couplings. I'm not quite sure how to pronounce it, but that one right there. But in terms of just kind of an overview of what this is going to look like, and just to kind of just mark up this little diagram because it's likely to be on our test. So a key thing to look at is the charges of this metal, and those are kind of going to be our giveaways as to what is happening. So right here, we're going to focus on that carbon, and this is an oxidative addition. When we move down, we're going to go down here and down this way and label a transmetallation. As we're kind of moving around, we're gonna see that change or consistency in the charge of the palladium, and over here we see reductive elimination when that argon and other reacting group leave. And then over here, when we do see this change in charges, that's primarily going to be due to a ligand association or dissociation. So this is where we would see a group that's associating or dissociating. This can also look like and hopefully we go a lot more in depth about the catalytic cycle because I don't completely understand it, but I think that's pretty much a good grasp on what we did in this first week of class. Thank you for watching this video.